So the idea of this class is to talk a little bit more about using Laplace transforms to solve ODEs, and in particular ODEs with discontinuities. So this is the example we're going to look at. We're given a linear second order ODE with some initial conditions, and we're asked to use Laplace transforms to produce the solution to this problem. Now in particular, the right hand side, this R of t, isn't explicitly given, it's just given through a picture. Okay? So this kind of question, you're not explicitly given your right hand side, your R of t, but you've just got a graph of it, of the function. Okay? So we're going to look at how to solve this problem, and essentially the solution method incorporates lots of different elements from this section on Laplace transforms. So it includes transform of derivatives, using a table, second shifting theorem, and also Heaviside step function. So lots of elements are incorporated into this particular example. In particular, you'll see that the R of t has two jump points or two discontinuities in it. And let's say you wanted to use different methods. Let's say you didn't want to use Laplace transforms. Let's say you used undetermined coefficients. What you would have to do is solve three problems. You would have to solve this problem from 0 to 1, then formulate new initial conditions, solve this problem from 1 to 2, and then solve the problem again from 2 onwards. Okay? So this is one of the advantages, in my opinion, that Laplace transforms play. They simplify everything in a reasonable way. They're not always the best way to go, but for a problem like this, they're pretty good. Okay, so don't worry if you haven't got this totally written down. I'll put it back up in a second when we start working on it. So just to refresh our memory, the Laplace transform is an integral transform involving this multiplication with an exponential, and you form this improper integral. So everything here is a function of s. So this is the definition of a Laplace transform. Now we've looked at the Heaviside step function. You can see it's defined here, and then this definition is just shifted along a units. So you can see that essentially at our point of interest there's a jump occurring. To the left of that point the function's 0, to the right of that point the function's 1, and at the jump point the value's kind of the average of the jump, 1/2 in this case. Now remember, the jump point, the definition of the jump point is not a big deal. It doesn't change anything with transforms or anything like that, okay? We've just decided to define the value at 1/2, or a in this case, to be 1/2. Okay, that's just, you don't have to have it that way. Now when we're solving differential equations, the following identities are very important. The transform of derivatives. So here it is for first derivative. You can think of, say, f of t here being the solution to your differential equation. And we've also been looking at this table, and in fact in the solution for this example we'll refer back to this table. Okay, so let's have a look at our problem. Now the first thing I'm going to do is actually write the R of t in terms of Heaviside step functions. Okay, so what I like to do is break the graph up into bits. Okay, so let's just consider the first jump point. To the left it's 1, to the left it's 0, and to the right it's 1. So actually from say here to here, the portion that you can see, that curve is covered by just the regular Heaviside step function, u of t minus 1. Okay? So let's just write down that portion. Okay? So up to here, say I'm okay. Now what happens if I get to 2? Well, the graph jumps from positive 1 back down to 0. So in a sense, the function has been switched off back to 0. So to do that, what I can do is take something away from this. In fact, I can use another Heaviside step function. Okay? So let's just check to see that this definition makes sense. Okay, to the left of 1, this is 0 and this is 0. So that's okay. Right? Between 1 and 2, this is now 1 and this is still 0. 1 minus 0, 1. To the right of 2, this is 1 and this is 1. So 1 minus 0, 0. Okay? So it's important to be comfortable with going from a graph to some sort of description in this context, because I want to take the transform of r of t. Okay. So what we're going to do, and a general step for solving these problems, is to take the transform of both sides of my original ODE. Then apply transform of derivatives and initial conditions, rearrange everything, and solve for the transform. Then untransform everything to get the original y of t back. Okay? So what we're going to need here is a little bit of manipulation. So you might want to just sort of leave a gap, or you can write it down straight afterwards if you want. We're going to need a few computations involving partial fractions. So I'm going to sort of put those on a different sheet. Now, there's no way to tell this, of course, when you start the problem, but because I've solved the problem, I know that this, we're going to want to take the inverse transform of this form. Okay? And in classes, what I try to do is, I say, okay, let's take a common sense approach. Try to, if you can, fool with the numerator and see if you can simplify it. But that's not always possible. Okay? So what I wanted to do was spend a couple of minutes talking about a very direct way of using or applying partial fractions. A very direct way. It's called the Heaviside method. Not to be confused with the Heaviside step function. Okay? Now, let's say I have something like this. I can't quite see how to play with the numerator for that one. You might be able to, but the standard partial fractions expression is something like this, where big A and big B are constants that we want to determine. Okay? The factors down the bottom are linear and they're not repeated, so we can have this kind of expansion. Now, I can show you how to calculate A and B in one line. Okay? One line. But this is important, okay? So if there's one thing you want to know about partial fractions, this is it. Okay. So you've got to pay attention now. Suppose I wanted to calculate big A. All right? Big A lies above s minus 1. What I do is I just concentrate on this left-hand side and cover up s minus 1. Right? Then I plug in s equals 1, and that gives me the value of A. Okay? So you look down here. Let's say I want to calculate A. A lies above s minus 1. So I go over to my left-hand side. I cover up s minus 1 and plug in s equals 1. Okay? So if s equals 1, I've got 1 on the top and minus 1 on the bottom. So what will A be? Minus 1. Okay? Pretty good, huh? Let's say I wanted to calculate B. B lies above S minus 2. So I go over to my left-hand side, I cover up the S minus 2 and let S equal 2. So what's B going to be? 2. Right? If I put S equals 2 there and S equals 2 there, I'll get B equals 2. It's called the Heaviside cover-up method, due to Oliver Heaviside. Now, Heaviside was criticised in many cases for not formally justifying a lot of his working. This can be formally justified, but I'm not going to do it. Okay? So, it's called the Heaviside cover-up method. Okay? So let me just go through it one more time. Suppose I wanted to calculate A. A lies above S minus 1. So I forget about the right-hand side. I go over here. I cover up the S minus 1, and I substitute S equals 1. I'll get 1 up the top, minus 1 down the bottom. A equals minus 1.
If it's S plus 1, does that make a difference?
No.
It's still 1.
Yep. Yep. So, you would sub in. So if it was A on S plus 1, you would sub in S equals minus 1. Yeah. Yep. So if I plug it, so I cover up, plug in S equals 1, I'll get 1 on. 1 on 1 minus 2, which is minus 1. Okay. Now, let's say I wanted to calculate B. B lies above an S minus 2, so I forget about the right-hand side, cover up the S minus 2 and plug in S equals 2. So I get 2 on 2 minus 1. You've got to love that. Okay? It'll work. It'll work when you don't have any repeated factors down here. So if you had S minus 1 or S minus 1 all squared, Heaviside won't work. Okay, well not necessarily. Okay, so he didn't get criticised for this, but he got criticised for other things. So there's another partial fractions in this question as well. So let me show you that one and show you how it can be done in one line as well. And this is even more difficult. Okay, so that's one. You also have the case where we want to take the inverse transform of the following. Okay, again, it's just linear factors down the bottom. Okay, there's no repeated, no squareds or cubes or anything. So it would be in the following form. Okay. So have a look at that bottom line. Let's say I wanted to calculate A. A lies above an S. So I go over to the left-hand side, I cover up the S, and I plug in S equals 0. So that's immediately going to give me A equals 2. Okay? Oh, 0. A equals a half, sorry. Now, let's say I wanted to calculate B. Again, B lies above an S minus 1. Go over here. Forget about that. Sub in S equals 1. So I'm going to get B equals 1 over something like minus 1. And over here, C lies above an S minus 2. Go over to the left-hand side, cover up the S minus 2 and plug in S equals 2. So I'm going to get something like C equals 1/2. Okay, so hence this form here. Okay, so it's A on S minus 1 on s minus 1 plus a half over s minus 2. Okay? 1 line. Well, 1 line for each constant. What do you think? It's all right? Anyone remember that from first year? Anyone? Yeah. I do teach it in first year. Whether or not people remember it is another matter. Okay, so you can, let's say you get something like this in the exam, you're welcome just to say, okay, I'm using the Heaviside cover-up method. With that out of the way, let's actually get back to our problem. All right? So what we want to do is take the Laplace transform of both sides, simplify it using the transform of derivatives and the initial conditions, solve for the transformed function, and then untransform everything. So let's take the Laplace transform of both sides. Now remember, the Laplace transform is a linear operator, so I can break it up into little parts. So this and this are the same, so all right, so now what I would like to do is use my transform of derivatives down here and calculate these transforms over here. And I can do that using a table. Okay, you can see in this line I've got the transform of the second derivative, transform of the first derivatives. And for the step function, I've got the transform over here for various values of c. Okay, so I'll put that back up again later if anyone needs it. So using a table, we obtain the following. Well, transform of derivatives for y double prime is this. The transform of y prime is this. And I've just got 2 times big Y of S. The transform of my 2 Heaviside step functions can be found in the table. Okay, and notice I've switched to big Y of S notation.
Is that a continuation of the same line?
Yep. Oh well, it's no. Yes, it is. Yep. So that's the transform of y double prime. That's the transform of y prime, and that's just the transform of y in the new notation. Okay. So now what we would like to do is apply the transform of derivatives. Okay, we've got these, incorporate the initial conditions. We've got these sort of conditions here. What we would like to do is simplify. So we can go back to my initial conditions and just look through and find y of 0 and y prime of 0 and substitute 1 and 3 in respectively. Okay. So applying the initial conditions, we obtain the following. Okay, well, y of 0 is 1, so that'll be 1, that'll be 1. Y prime of 0 equals 3, so that'll become 3 in there. Okay, well you can see a little bit of cancellation going to happen here. I can take that minus s to the other side, and then I can factorise. I can form, my aim here now is to solve the transform problem for big Y of s. Okay? So, rearrange to form the following. Well, that minus s is going to go to the other side, and then I've got a common factor of Y of s. Okay, well I can actually factor this quadratic and then take it to the other side. So now what I can do is say factorise that and then just sort of divide both sides by it. So I'll get the following possibly familiar form. Okay? All right, so we're actually have solved the problem now in the transform setting. Okay? So the challenge now is to untransform. Okay, so we need to take some inverse transforms. Now this is not always easy. And the reason is that if you look down your Laplace transform table, this isn't there, this isn't there explicitly, neither is this. But if I can use partial fractions on these representations, then I can actually break it up and form something I can work with. Also notice here, strictly speaking, this is there for big G of s here. And this is also there with big G of s there. So the second shifting theorem is going to be applied here. Okay. Now, using my partial fractions expansions that we calculated before. Now, of course, if you're doing this in an exam, you'd have to calculate them now, right? So you're probably a little bit frustrated because you've already done all this work. You just want to do it in as quick time as possible. So I can write it now as the following, okay, using my partial fractions expansions. Okay. So what I'm going to try to do now is take the inverse transform of each part of that. So I can easily calculate the inverse transform of this and this from a table. And now the challenge is to take the inverse transform of this term and this term. Well, like I said before, if you look at this, it's just a big function of s times an exponential. Function of s times an exponential. Okay, and the same with this one. This is the same function of s times a different exponential. Again, this is the form, the general form. So to actually calculate the inverse transforms of these last two big terms, what's driving it are the things in brackets. Okay, this function, this function. Take the inverse transform of this function, equivalently this function, to get g of t, shift it, and then multiply through by a Heaviside step function. It's the second shifting theorem. Okay? So let's take the inverse transform term by term. Now, it's good that these two are the same functions because it actually saves us a lot of work. Okay, these might look quite complicated, but it actually saves us a lot of time having them the same. Okay, so the inverse transform of this, well, that's going to be something like an exponential, okay, with a equals minus 1. So I'll get this term. And the same with this one. This is also going to be an exponential. And now what I want to do is take the inverse transform of this and then shift it and then multiply through by the Heaviside step function. Okay? Now, because there's a e to the minus 1s, that's actually the value of the shift here. So if I apply the second shifting theorem, it's this times the inverse transform of all of this shifted 1 unit. Okay, so what's the inverse transform of this? Well, it's 1/2. Again, you can look that up on the table. Okay, if I shift the constant function 1/2, it's still a half. So that doesn't change at all. What about this one? Well, the inverse transform of that is going to be something like an exponential, right? But I want to shift that exponential 1 unit. So the inverse transform of this isn't going to be something like e to the t, it's going to be e to the t minus 1. And for this one, again, similarly, it's similar to the previous one, it's going to be something like an exponential, but not e to the 1/2 e to the 2t, it's going to be shifted. So it's going to be 1/2 e to the 2 bracket t minus 1. Okay? Now for this one, this is exactly the same in brackets up here. The only thing that's different is the 2. So again, using the second shifting theorem, the c would be 2 here. So instead of shifting everything 1 unit like we did up here, we'd shift it 2 units. Okay, so that should be a plus. And then minus, so this will be u of t minus 2 times the same transforms just shifted 2 units. Okay. Now that's a long question. Agreed? You've got to be on top of everything for a question like that. You've got to know the method for solving ODEs. Then you've got to know how to apply the transform of derivatives, incorporate the initial conditions, partial fractions, and then inverse transforms.